Let's start this again. All right. One announcement. So for assignment 1, can you submit the hard copy? It's due next Wednesday, but you can also submit it on Monday. Or there's a box in room X235. Use hand in for the code, though, so that we can check it. But the TAs will mark what you hand in. So you have to put a hand in. So the physical hard copy that you hand in is the thing that will get marked, and we'll just check the other thing, the other code. All right. So if you want something marked, put it on the hard copy. There's details on the web page. And the midterm is still the same. I just left that announcement there. Does anyone have any questions about anything? Okay. Oh, I'm not there yet. So what we've done so far is we started all looking at this idea of agents act in environments. They have access to their abilities, their goals, preferences, their prior knowledge, the observations and the past experiences. Then search we use as abstraction for finding paths in graphs. They differ in how the frontier is selected, so there's a whole lot of different algorithms all differed by how the frontier was selected. We had multiple path pruning and depth bound reduced the search space because we could reduce cycles. There were some paths that we disallowed. And then we looked at depth bound and how depth bound and depth first search can save space when it's used for iterative deepening and branch and bound. So that was sort of a high-level summary of where we're at so far. Are there any questions about any of these things? Okay. So let's start off with a couple of clicker questions, and thanks to the people who've been posting questions. The first one is, why might A* search with multiple path pruning not be admissible? A, it always expands the path on the frontier with the lowest F value. B, it will not return the lowest cost path if that path led to a node that was already expanded. C, it is always admissible. D, it only considers the heuristic value and not both the path cost and the heuristic cost. Or E, it uses space exponential in the path length. Okay, how are we going here? Does anyone need more time? Someone who hasn't sat down needs more time. A few people. Does anyone still need more time? Can I stop? How are we going? We're at 99, 100. Let's go with 100. Okay. Right, good. The answer is B. It will not return the lowest cost path if that path led to a node that was already expanded. Remember, so if you might have a lowest cost path, but it got stuck before, and that's why we needed the monotone restriction. Any questions about that? Okay. Next question is, what is not a disadvantage of dynamic programming? A, it must recompute the cost to go for each new goal. B, it has to store a value for each node and so cannot be used for enormous graphs that are generated on demand. C, it can potentially store wrong costs leading to errors when returning optimal paths to goal, optimal paths to the goal, to a goal. It cannot be used, or D, it cannot be used for graphs in which it's difficult to compute the inverse of the neighbor's function. So this is not a disadvantage. Let's wait till we have 100 again. Does anyone need, anyone still need more time? Okay. Let's stop this. Oh, that's exciting. The answer is C. But lots of people said B. And lots of people said everything. Let's talk about all. Good. is what we like. So what happens is that when you have a new goal, you have to recompute the optimal path, right? As you change your goal, you have to recompute this cost to the goal. So whenever you have a new goal, you're going to recompute this value. Okay, so that is a disadvantage for when you change your goal. It essentially has to store every node. And if you look at the graphs that we saw before, that are just some of these enormous graphs, then you just can't store all of them. So the problem of actually storing a value for every node, you can't store a lot of these enormous graphs. Because a lot of the things we're looking at so far, when we talk about exponential space, we mean the cases where we're not actually storing the graph, we're just generating it on demand. So storing the whole graph is something we want to avoid. C, it doesn't store wrong costs. If you effectively do this least cost search backwards, it always just keeps generating them in order. And it requires finding nodes going backwards from a node. If you've only stored the neighbors, which all you need is for the represent a graph, so you can't use it when you're doing the inverse. Okay? Any questions about that? All right, good. Right. So which of the following is not true of constraint satisfaction problems? A, newspapers regularly publish constraint satisfaction problems for people to do. B, a constraint satisfaction problem is defined by variables, domains, and constraints. C, a constraint can tell us whether an assignment of values to some of the variables is legal. D, the domain of a variable specifies the values that the variable can take. Or E, there's only ever one way to define a problem as a CSP. All right, does anyone need more time? Hands up if you need more time. Okay. Yes. The answer is E. We did this. Everyone should have got this right. I like these questions because it lets people review the summary of what we've done, so now I can avoid it. Okay. Anyone have any questions about any of these things? All right. So what we did at the end of last time, we ended up having this constraint satisfaction problem is defined by a set of variables. Each variable has a domain, which is a set of possible values. We're going to assume now they're finite. Although we don't always assume they're finite. Some of the times we have continuous domains. And the possible world's an assignment of value to each variable. And what I'm going to have is this is slightly more refined than I did last time because I just wanted to show some examples. A scope is just a subset of the variables, and a hard constraint on a scope specifies which combination of the values of the variable and the scope are legal. So it's a function from the scope into true, false. So if I have the constraint A is less than B, the scope is the set of variables that involves A and B, right? And it's a function essentially from A and B into truth values. So if A is 0 and B is 0, then the answer is false, right? If A is 0 and B is 1, the answer is true, right? If 1, 0, it's false. For 3, 17, it's true. Right? So it's a function from values of A and B into the truth values. Does that make sense? It's just a function. All right. Questions? No. So the first algorithm we'll give is generate and test. So what we can do is we can generate the assignment space you could generate the cross product of all of these domains, and you're going to test each assignment with the constraints. So if we have variables A, B, C, D, and E with 4 values on each with value 1, 2, 3, or 4, then we end up with this space. And how big is this? How big is the assignment space? Quick. 4 to the 5th, right? It's 4 times 4 times 4 times 4 times 4, so it's 4 to the 5th. So how many assignments need to be tested for n variables, each with domain size n? N variables, each with domain size d, d to the n. Right? Don't try and remember this, just work it out every time. I don't remember all these formulas, otherwise you get it mixed up. It's just d to the first times d to the second times d to the third, and there's n of them, so it's d to the n. Right? All right. No one uses this, right? This just gets too big and this just explodes too quickly. The problems we're going to look at are just too big to do this. So what we can do is we can instantiate the variables one at a time. And what we're going to do is evaluate each constraint as soon as all of its variables are bound. So if we have the constraint, so the example I'm going to do is, first one I'll do is A is less than B and B is less than C. And the domains are 1, 2, 3, 4. 1, 2, 3, 4. So what we could do first of all is we could first of all assign A. A is 1. A is 2. A is 3. And A is 4. Okay. And then we could expand B. B is 1, B is 2, B is 3, and B is 4, right? And what can we do here? Is there anything we can do, given these two constraints, is there anything here we can prune, evaluate? Is there anything we can evaluate? Yeah. Right, so you can prune this. Right? And what about this one up here with B is 1, B is 2, B is 3, and B is 4? What can we do here? You can prune all of them. Right? Does that make sense? Because all of these, ignoring this one, all of these violate that first constraint. So in fact, we can prune off more than half of them at this stage. And then we can start looking at C. So we could do C here. C is 1, C is 2, C is 3, and C is 4. And what happens to all of these? Right, they all die. Okay. Is that okay? All right. So here's what we're going to do is we're going to formalize this as a graph searching. So what we're going to do is each node here is going to correspond to an assignment of values to some of the variables. So this one here, we've assigned no values to any of the variables. Okay, so this one here is going to correspond to this empty assignment. And this one here is going to correspond to the assignment A is 1. And this one here is going to correspond to the assignment A is 1 and B is 2. Right, this node here. And suppose we have a node with some assignment. All we're going to do is we're going to choose some other variable to split on. So the node, so if n is a node with some assignment, we're going to select a variable here, we're going to select b that isn't assigned, and then we're going to, for every value of that variable, there's a neighbor. Right, so at this point here, we're going to select a variable that hasn't been assigned, and for every value for that variable, there's a neighbor. For here, we're going to assign a variable that hasn't been assigned, which is c. We're going to, for every value here, we're going to assign a value. And all we're going to do is evaluate the constraints as soon as we can. Right, so a is 1 and b is 1 here. Once this is assigned, once we've assigned a and b, we can check this constraint. The start node here is the empty assignment, and the goal node here is an assignment that satisfies all of the constraints. We don't have one yet, do we? We can build one here. So C is 1, C is 2, C is 3, and C is 4. Are any of those solutions? Are any of those nodes down here solutions? Which ones? Right, so this is a solution. This is a solution. And this is not, right? So we can actually go down here, and we can effectively do backtracking search. It's the easiest way to do this, is we can go down here and keep searching this space, just exactly the algorithms we used before, until we found a solution. Okay, this is much more efficient than generate and test. Right? We can just generate a few of them until we find a solution. Okay, questions? Now this search space here depends on which variable is selected. So if we have those constraints, which variable should I select first? So I got this one. This is my problem I'm going to look at. So I selected here A, B, and C, but I didn't need to. What if I selected first split on A, and then I split on C, and then I split on B? Is that a good ordering? Right, so this one here is a terrible ordering because there's no pruning. Right here, you can't prune anything. If you split here and split here, there's no pruning we can do. We can't evaluate any heuristics. Right, so this one here, in this point here, we can't prune any node at this level. And all the pruning happens at the bottom, which is effectively just as bad as generate and test for this example. What could we split on? What else might we try? Go from start at C, go to B, go to A. Why? Because then you just reverse the constraint. But that's the same as this, isn't it? Can we do smaller than this? Do better than that one? You already know certain values. We'll do that in a minute. I'm just doing the orderings. Don't you can do better than the one on the right? Hint, it's not C because it's symmetric between A and C. So what might it be? Yeah. Yeah, well, B at the top. You don't have much choice. Right, B is 1. 1, 2, 3, and 4. And why might we split B at the top? Let's do B as 1. What might you split here for? We want to prune. Remember, we like pruning things. All of the A's can't be there. Right, so we must split on A here. Right, 1, 2, 3, and 4, and we can prune all of those. Right, what about on this right-hand side here? Why? You can split on C here. Is that right? Oh, sorry. Right, so each of those can be pruned. Because C is 1, 2, 3, and 4 are all inconsistent with B is 4. And now we can do B here, which again we might as well split here on A. 1, 2, 3, sorry, might as well split here on A. 1, 2, 3, and 4. Actually, A is 1, A is 2, 3, 4. Oh, let's split on A. Right, again, we can prune. What can we prune? 3 and 2, 3, 4. 2, 3, 4, right? Because A is going to be less than B. B's 2. And then we can go here to C. 1, 2, 3, 4. What can we prune? 1 and 2, right? Is that right? And here are 2 solutions. Any questions about that? Yes? Why can't we? Here? Because we can't evaluate either of these constraints at this stage. We've assigned A and we've assigned C. We can't evaluate this constraint because we don't know what B is, and we can't evaluate this. The rule says that we can only evaluate a constraint when all of its variables are assigned. Oh, this algorithm is much dumber than that. All we're doing is just evaluating constraints as soon as we can. We're not doing, that's actually complicated. You have to do theorem proving-y type things to prove that. We'll get to that, but that's actually complicated, yeah.
The algorithm to the left, when we set B equals 1, the next node we decide to expand A, and when we set B equals 4, the next node we decide to expand C. The reason we did that is because those choices prove the highest amount of paths. But how would an algorithm determine that? How would it determine that when B equals 4, it should expand C and not A? Do we use heuristic for that?
The algorithms that exist, all their work goes into choosing variable orderings, using all sorts of heuristics and these things. So these big algorithms that exist, nearly all their work is trying to choose these variable orderings that prune as quickly as possible. We're actually trying to fail as fast as we can, which is sort of ironic, because we don't want to get to this stage here. Everything's looking really nice, and then all of a sudden we have to prune a whole lot of things at the end. Yes, a lot of the work is going into actually just choosing the elimination orderings. Let's go. All right. Oh, this is the one we did. How am I going? Okay, let's. So there's the first example we did. What the second example we did is there's a few more variables. If once we get another variable, it turns out there's only, how many solutions are there for this? Yeah, there's one solution to this, right? But it's complicated for this algorithm to find that one solution, right? Because we might split on B first, then A, then C, then here we've got to split on D, right? So some of these are going to be inconsistent. What about this example? This last one, A, B, C, D, E. There are no solutions, right? And so the algorithm we've seen so far, this is sort of it doesn't actually work so well for 2 and 3 because it sort of keeps splitting these things. And somehow it'd be nice to get an algorithm that's a bit smarter than just branching on these things. One of the problems that occurs here is that the relationship between B and C keeps getting rediscovered for multiple times. So if we split here on A again, right, we're going to prune C as 1 again because of B is 2 and B is 3. We're going to keep pruning them in different parts of the search tree. So what we'd like to do is get an algorithm that can do better than that. All right, let's skip that. So what we're going to do is we're going to do something, we're going to try and prune domains as much as possible. The idea we're going to try and do now is we're going to prune the domains as much as possible before we start selecting values. That's going to be the intuition that we're going to do. Instead of just selecting values at sort of arbitrarily here, we're going to start saying, well, hang on, maybe we can prune values. We can prune this value for, once we've pruned the value of A is 4, or once we've pruned the value here that B can't be 4, right, we don't want to keep rediscovering it. We'd just like to say, let's prune it once and get rid of it and then not think about it again. So the first thing we'll do is domain consistent. If no value of the domain of the node is ruled impossible. So a variable is domain consistent if no value of the domain of the node is ruled impossible by any of the constraints. So let's look at this. Whoops. I'm going to go backwards, not forwards. So is there any value in here that can be ruled that is not? Is there any value of any of the variables here that we can just rule out a priori as being impossible? So we're going to rule things out just straight away. It's obvious that we can't have. What's obvious that we can't do? Which domain can we prune straight away? Yeah, B is equal to 3. We can prune these things. The first thing we're going to do is just go through and just prune everything that's inconsistent with what we have. And you might think, well, obviously we just don't put it in the problem. But what often happens is we set up a problem and then we make observations of it and we just want to rule out all of those things that are inconsistent with our observations. Someone tells us something new, we just want to rule it out from the domain instead of searching for it and using anything else. So that's sort of pretty trivial. All right. So now what we're going to do is we're now going to give another way to do things. So before we do that, we're going to define something called a constraint net. Constraint network. So for a constraint network, for A is less than B and B is less than C, we're going to write a node for each variable. So there's a node A and a node B and a node C. Right? Now we're going to do, then there's a rectangular node for every constraint. So a constraint is A is less than B and B is less than C. And there's going to be a domain of values associated with every variable. So here I'm going to write it underneath 1, 2, 3, 4. I should have written bigger. 1, 2, 3, 4. 1, 2, 3, 4. I'll write it under there. And there's an arc from each variable to the domain to each constraint that involves it. So because A, there's going to write an arc from A to B, an arc from B to A is less than B, and that. Does that make sense? I just have a rectangle for every, there's an arc from every variable to every constraint that involves that variable. And we're going to write in there, what we're going to follow is we're going to write this arc as this pair between the node and the constraint. So we're going to write this as a pair. When we write down algorithms, we're going to write this arc as a pair. A is less than B, and B, so there's going to be a pair, A is less than B, and B, A is less than B. Right, so that's how we're going to write this arc and this arc. Okay, just when we write this algorithm, and if we have three variables, x plus y is equal to z might be a constraint, between the three values, we could just write, we need to have the three variables that involved x, y, and z. There's going to be three arcs. Okay? So here's my constraint network for this other previous problem, is that I had, for this problem here, I have A, B, C, D, E. They each have 1, 2, 3, 4, and then all these constraints like E is less than C. And we end up with a network that looks like this. Okay, so the nodes here, the square nodes are the variables and the rectangular nodes are the constraints. Is that clear? Okay. Now here's the most important definition we're going to give for this week. So an arc between x and some relation between x and other variables is arc consistent if for every value x in the domain, little x in the domain of big X, there's some value y in the rest of the variables in the domain of the rest of the variables such that R of x, y is satisfied. So let's look at this graph. So is A is less than B arc consistent? So what do we need? We need for every value of A, so A can be 1, 2, 3, or 4. A can be 1, 2, 3, and 4. Is there a value for B such that this is consistent, true? Is there a value for B that satisfies this? Right, there is. So in fact, B is 2 satisfies it. So we've got to check all of them, right? 2, what about 2? Is there a value for B? Yes. Right, so B is 4. What about for A is 3? Is there a value for B? Yes. So these. What about for A is 4? No, right? So is this arc consistent? So there is no value, right? Is it arc consistent? No, right? It's not arc consistent. So what are we going to do if it's not arc consistent? What can we do? In this case here, if it's not arc consistent, what can we do in this case? You can prune the 4, right? 4A can't be 4. We've just locally we've looked at this constraint and said A can't be 4. Okay, we're going to prune it. So a network's arc consistent is full of arcs are consistent. Now what if arc's not consistent? Then all values in the domain for which there isn't a corresponding value can be pruned, can be deleted. And we're now going to just repeatedly do this. So let's actually go through and look at this. So we have this on the AI Space website. There's this little constraint, is the Constraint Applet, which does this for us. And this is the arc that says between A and A is less than B. What's it going to do here? It's going to, this is the one we did here, so what did it do? It's going to prune something from A. What's it going to prune? 4, right? So if I press on this arc, it's going to prune 4 from A. So if you see what I did, oh, that just does it, or this, it just displays what I just did here. Right, what if I now do, A is less than B? What if I click on this arc here? What's it going to do? Is it going to do anything? Oh, sorry, by the way, it also changed this to green. So green, it's now arc consistent. Once you prune it, it's arc consistent. If I do this, it's going to remove 1 from B, right? What if I do this one? What if I do this one here? B, this one on the right. What's it going to do? Prune 1 from C. Oh! Oh, what did it do then? Hmm? Yeah, there's no 1 in B, so prune both 1 and 2, right? What if it happens if I do this one here? What's it going to do? It's going to prune 4 from B. And what else happened here? Hmm? Hmm? Oh, you made this other arc. They all nicely turned green because they're all arc consistent. And now we have this other arc, which is now blue. Why is it blue? Right, because why is it blue? Because it might be consistent, right? Inconsistent, right? We've reduced the subdomain size of B, and so now we might have to reconsider this. Right? Before we knew it was arc consistent, and now we can do that. And once we've done that, we've reduced all the domains, and now we can stop. Does that make sense? Any questions about that? So is this general arc consistency algorithm we're going to do. As the arcs, we're essentially going to consider them in turn, making them each arc consistent. And now the question is, when an arc's been made arc consistent, does it ever need to be checked again? Well, we just saw that, so the answer is yes, it does. So this arc of x and r of xy needs to be revisited if the domain of one of the y's is reduced. So we might need to reconsider this. So once we've removed, this has been made arc consistent, it's going to remain arc consistent unless one of the y's has its domain reduced. And effectively, we're going to keep track of this, and then we're going to revisit them only when this occurs. So here's the algorithm. So for each variable, we're going to set up this d of x, which is the starting off initially the domain of x, and then we've got all of the to-do arcs. The TDA is the arcs I'm going to do in the future. So I'm going to start off with all of the arcs. So it's a pair of x and c for every constraint c and for every x in the scope of c. And then it's going to loop through, and while there are no more arcs to do, I'm going to select and remove an arc. Oh, it should say arc from TDA. I edited the previous, all right. It should say, select and remove this arc, xc from TDA, from the to-do arcs, and suppose the scope of this c is, it contains x, and the other ones are y1 to yk. Then we're going to get the new domain of x, is a set of x such that there exists some values of all the y's such that the constraint is true. Right, so what we're going to do is if there exists some the values of all the other y's such a constraint is true, we're going to put it into the new domain of x. And we have to do something. If the new domain of x is different to the old domain of x, we may need to add some more arcs on. Okay? So that's the algorithm that we just showed in that previous example. And we're going to keep doing that until we find out that the to-do arcs is empty. All the arcs turn green. Okay. So let's look at a bigger example. Let's file. I think it's scheduling 1. That's not very good, is it? Hang on, I think let's make it large. I'll hide that. All right. Let's make sure nothing overlaps. Is that okay? All right. So this is the same graph we did before, and you tried to do this by hand, just by looking at this, and it was really difficult to do here. So what if I press on this arc here? There's one on the bottom left here. What's it going to do? It's going to prune something. It's going to prune D. What's it going to do with D? What's the illegal? What can't D be? 1, right? So it's going to prune that. So it's going to get that, and it's going to prune 1. Okay, let's move. What's happening here? It's going to prune 4 from E, right? What's this one going to prune? Nothing, right? Because it already was arc consistent. What about this one here? C is less than D. Where it's going to prune 1 and 2 from C. What if I click on this one? What's it going to do? Anything? E is less than C. Can we prune C? What can we prune here? And this one here that's flashing where my mouse is. What are we going to prune? I'm going to move 1 from C, okay? What if I click on this one? What's it going to do? C is less than D. What are we going to do? We're going to prune what from D? 2 and 3. So it's only going to be 4. Right, E is less than D. What's it going to prune? Nothing, right? I think. All right, now we can prune. A is equal to D, so we can prune that. And we can prune A is different to B, so we can prune 4 from B. We can keep. Where's E is less than C? That one? All right. Then I have to prune this one again, do I? And in fact, it doesn't actually matter. I can do it in any order. The algorithm doesn't care. And so it turns red, flashes red when it's. And eventually, it stopped and checked it. And there's one solution to this problem. Still have to do one more look. All right? Does it make sense what the algorithm is doing? It doesn't matter which order you're going to do it. There's just all these to-do arcs. And we're just going to visit each one of them in turn. And it's going to start pruning what's going on. Yes?
How does it know it has to revisit some arcs?
All right.
So how does it choose which ones to?
It revisits all of the arcs. Let's go back to that. Oh, I'm lost. Where am I? There. Let's go back here. So this arc between x and some relation of x and y, when it's been made arc consistent, it's arc consistent until the domain of one of the y's is reduced. When the domain of one of the y's is reduced, we no longer know whether there's an x that exists, right? So then we can have to revisit it. So this is sort of the only rule you have to follow. So in the code, there's sort of a positive way of saying that given a y, you've got to find the x's. But it's easy to think in this terms of given the x, you've got to revisit it when you reduce one of the y's. Okay. So does this always solve problems? Does this always solve the problem? No, right? Doesn't always solve the problem. In fact, the very first example we did didn't solve this problem. For this one here, I think is this one. Right, if you look at this one, it doesn't solve the problem. It's too slow. Right, so this one here, it doesn't always solve the problem, but simplifies it a great deal. Okay, so although it doesn't always solve the problem, it's going to simplify this a great deal. And we're going for time here. Okay.
Why is that not a solution?
What?
Why is that not a solution?
What's the solution you're thinking it is? A solution is assignment of value for A, B, and C. Oh. Okay. All right. That's a good question. Here's an example. So if we have A is not equal to B is not equal to C, and C is not equal to A, and each have domain zero and 1. Right? So is it arc consistent? So for every value for A, is there a value for B? Where it's A is not equal to B. For every value for B, is there a value for A? What about this way around? For every value of B, there's a value for C, and every value for C. But is there a solution? No, right? So you actually don't know from the fact that it stops being arc consistent. Although we've simplified the problem, we haven't actually solved it. So it's yes, but there's no solution. Okay. And we'll talk about that next time. Any questions? I have assignment 1 here. It's 0, I mean. I can't count. I'm putting it in piles corresponding to the first letter of your last name. I'll put them down here so you can find them.